Hello everyone, my name is Priyansu Kumar and I am going to give a presentation on my topic Active Disturbance Rejection Control of a SEPIC converter. So this is the circuit diagram of a SEPIC converter where we have two inductors, two capacitors, a diode and a MOSFET or a switch. So SEPIC converter usually provides a non-inverted output and it has high efficiency, reduced ripple currents and low voltage stresses on the switching devices. SEPIC converter is actually a buck-boost converter that can operate both in buck and boost modes of operation depending upon the duty cycle provided to it. That is, when the duty cycle is less than 0.5, it operates as a buck converter, when the duty cycle is greater than 0.5, it operates as a boost converter. Actually, this converter is a fourth order system, so the design of a controller for this converter is a tedious task. These are the specifications of the converter that I have designed according to a switching frequency of 100 kHz. This has led to me the reduction of component size and losses attached to them. So the transfer function of the converter has been calculated by using small signal analysis and neglecting any parasitic resistances, and hence the transfer function calculator is shown in equation 1. Now the reduced order modeling of this converter. So when I applied the ADRC control method to the normal transfer function of this converter, then it was seen that the output is very sluggish. This is because of the ESO formed in this converter in this controller due to the fourth order system was of a fifth order. So that led to the more number of integrators, and this led to the phase lag that caused a sluggish response. And due to this, the disturbance reaction capability also reduced as controller took more time to understand the type of disturbance. Hence, we can see that increased settling time and lower disturbance reaction capability was achieved. So the order of the converter was reduced by a method called balanced truncation method. So in this, this method was generally given by Hermann Hankel. So accordingly, the method was to obtain Hankel singular values based on the controllability and observability gramium. So first, the balanced reduction of the system is done to isolate the states whose contribution to the input-output responses is negligible. After that, the reduction of the system, Hankel singular values are calculated, which are in smaller entries. So accordingly, the Hankel singular values provides a measure of energy for each state in the system. So Hankel singular values are calculated as the square roots of the eigenvalues. So this is the reduced order model that I achieved by using the method that I explained here. So this is actually the second order system that resembles the fourth order system of the same system. So this is actually the reduced order system of this model. Now the ADRC control mechanism. In this method, we see that we are accumulating all the types of disturbances, whether internal or external, together, and it is cancelled in real time. So here also, first of all, we are converting the system's equation in this form as shown in figure 3. This is the implicit input-output equation of the converter, where U is the control signal and V naught is the system's gain, and all other terms are accumulated in this form. We are going to convert it into a state space model. So the state space model can be converted like this as shown in equation 4. So in a state space form, we can write as in shown in figure 5. So where A equals to this one, B is this matrix, and C is this matrix 1, 1, 0, 0. So the ESO or the extended state observer is formed as shown in figure 6, where L0 is equals to B1, B2 and B3 in this form is the observer's gain. So the controller is selected such as U0 equals to U minus Z3 cap upon V0, which can be written as KP R cap minus Z cap. So this is the standard form of the controller which is selected in ADRC methods. So now the tuning parameters are selected for independently for the controller and observer. So the characteristic equation of the controller is equated to the second order equation tuned in the form of controller's bandwidth. So this is given as determinant of SI minus BKP equals to S plus omega C equals to whole square. S plus omega C whole square. So this is tuned in this way. So these are compared, and the values of K1 and K2 are calculated as 2 omega C and omega C square respectively. Similarly, the characteristic equation of the observer is compared with the third order equation tuned in the form of observer's bandwidth. And similarly, comparing as was in controller form, the comparing we get beta 1 equals to 3 omega naught, beta 2 equals to 3 omega naught square, and beta 3 equals to omega naught cube. Now the stability analysis has also been done for the closed loop system along with the controller. So so the closed loop controller structure of the ADRC controller is shown in figure 3. So for performing the stability analysis, we need to have the ESO transfer function. So the ESO transfer function has been calculated as shown in equation 10. This is in the form of all the controllers and observers bandwidth. So and gain also, that can be written in further in the form of gain. So K1, beta 1 and all these gains are included in this one. So from figure 3 we can write as US equals to GCS RS minus GCS HS into YS. So comparing the above two equations, that is equations 10 and 11, the values of GCS HS and GCHS are calculated, and these are used to calculate the maximum sensitivity value. So the tuning parameters are selected such that the maximum sensitivity function MS lies in a standard range of 1.3 to 2. In this work, MS is calculated as 1.48. So ADRC methods are tuned by proper selection of controller and observer bandwidth such as to achieve the desired specification of output response. So there is a general common thumb rule that relates omega naught and omega c. So this is the thumb rule is that omega naught must be greater than equals to n omega c. So selection of n is important here. So by using the integral absolute error method on the calculation of this IAE, actually the value of n was selected as 14, and so accordingly we can see from table 2 that when the omega c is varied, so IAE is decreasing. So when omega c is actually increasing, the IAE is decreasing. So at the value of 900 I am getting the optimum value of omega c. Because after omega c equals to 900, we can see that at 950 the value of IAE is further increasing. So value of omega c is selected as 900 with n equals to 14. So simulation results. So the simulation results has been done for both the boost and buck modes of operation, but here I am showing only the boost mode of operation. This one is the servo performance, where the reference voltage is set to a some value and the controller tracks the output to that value. So in this case, actually the initial value of the reference was set at 60 volt, and at time t equals to 0.2 the reference was changed to 70 volt. So here we can see that the output settles immediately to the 70 voltage with with the settling time of around 0.02 seconds. So in this figure we can see both the output voltage V reference and inductor currents and output current. So in this slide we can see the effect of varying input and varying load on the output voltage of the converter. So in figure 6 we can see the effect of varying input on the output voltage of the converter. So at time t equals to 0.2, the converter's input voltage is changed from 48 volt to 80 volt. That is, the converter is now working. The working mode of this converter is in boost buck mode. So initially it was working in boost mode, and now after time t equals to 0.2 second it works in buck mode. So we can see the effect of this change in input voltage. So there is a transient in the output voltage that diminishes just in 0.01 seconds, and again at time t equals to 0.3 seconds the input voltage changed back from 80 volt to 48 volt or 48 volt, and again there is a slight dip in the voltage. Initially it was a slight increase in the voltage, and that settles down due to the increase in the input voltage, and now there is a slight dip in the voltage that settles again in 0.01 seconds. So this is the regulatory performance that shows that the output voltage remains settled whether there is an increase or decrease in the voltage, or there is a variation in the input voltage of the circuit. Now for the varying load condition also we can see that the output voltage remains settled at the set point value whether we increase the load or decrease the load. So at time t equals to 0.2 seconds the resistance value has been decreased, that is the load increases, and this can be seen from the effect on the output current and input current. So output current increases with the increase in the load, and so as the load increases there is a slight dip in the output voltage, which again settles back in 0.01 seconds, and again at 0.3 seconds the load has been decreased, that is the resistance value has been increased back from 50 ohm to 100 ohm, so the current decreases. So this slide clearly shows that the effect of varying input and varying load does not affect the output or the set point output that has been set for the converter. So the converter tracks the set point whether there is a varying input or varying load. This proves the system is, or the system with the controller is a robust system, and also I have earlier proven that the system is a stable system. So the tuning parameters are selected such that the settling time should be lesser for the system. So from this we can say that the ADRC control method has been successfully implemented on this converter, and with the use of ADRC control on this converter, the converter proves to be to give a regulated output voltage as and when desired by us, and this converter with the application of ADRC control can be used to integrate the PV system, or for the battery charging applications and any other such applications where we need a regulated output according to our desire. The hardware implementation of the controller, the hardware implementation of this system with the controller is also been done, but it's not been shown here. So that's all from me. Thank you.